Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu, and today we're going to talk about the last topic in Chapter 8, trends in the periodic table. So we're going to talk about different concepts and their trends in the periodic table. So first, atomic size. We have so many atoms in the periodic table. So with their atom sizes, there is actually a trend. So if I see a periodic table here, going from left to right, the same column, the size of an atom decreases. And that is because the effective nuclear charge increases, as we mentioned in previous video. Okay, and if we go down a column from top to down, the size of atom increases, and because there are more electron layers and more quantum numbers, more principal quantum numbers, right? So, and if you see this, and also the picture from the textbook, the largest atom will be found from the left column and in the bottom of the periodic table. The smallest atom will be found in the right column and top of the periodic table. So just give you an idea. However, all of these trends have exceptions. Okay, for the atomic size, the exceptions are in the transition metals, because due to the shielding of d orbitals or d electrons, the transition metal down to a group, the size period 4, the size of these transition metals in the period 4 is less than period 5, which is according to the rule. But period 5 and period 6 are have almost identical sizes of these atoms. So this is the exception. And also across the period, size shrinks for the first 2 to 3 elements in the transition metal, and then the size remain almost the same. So they are all due to the shielding effect of d electrons, and the exceptions of atomic size are transition metals. For all of the trends I mentioned in this video, you need to understand it, remember it, and also answer some of the questions of the trends if there are. Okay, so with this, and since we talk about the effective nuclear charge and how that can affect the size, you are expected to determine the size or compare the relative sizes of isoelectronic atoms or ions. The isoelectronic means whatever species has the same, iso means the same, right? Same number of electrons. So isoelectronic atoms with the same electrons, for example, helium plus has 1 electron, hydrogen atom has 1 electron. So these two are isoelectronic atoms. When we do compare the size of these species, the isoelectronic atoms or ions, we actually compare the effective nuclear charge, Z subscript EFF. And we can understand in this way. If they have the same number of electrons, then we don't need to care about shielding and penetration or whatever, because the electrons are exactly the same. What we really care about is how strong it can feel the attraction from the nucleus. The stronger the attraction, the smaller the size. So then we can compare the atomic number of the two species. The larger atomic number leads to a larger effective nuclear charge because there are more protons there, and there are more attractions to nucleus and leads to a small size. So here's a practice question. Which one has a smaller size? Oxygen 2 negative, anion, or sodium plus cation. Which one? So first, oxygen 2 negative has 10 electrons. The oxygen has the atomic number of 8, adding 2 more electrons because of 2 negative. In total, it's 10. Sodium, it loses 1 electron, so now it also has 10 electrons. These two species have the same number of electrons, so they are isoelectronic ions. When it's isoelectronic ions, we need to compare which one has more, has larger atomic number or has more effective nuclear charge. Of course, sodium has a larger atomic number, so there are more attractions of electrons in sodium, sodium ion, sodium cation, so it has a smaller size. All right. So besides comparing the size, we can also find the first ionization energy in the periodic table. The first ionization energy is the energy required for the removal of 1 mole of electrons from 1 mole of gaseous atoms. So in other words, it's the energy required for this equation, 1 atom in gas phase to become 1 cation, the corresponding cation carrying 1 positive charge and 1 electrons. Basically, it means you pull 1 electron from an atom. So the first electron you pulled are called the first ionization energy. Ionization refers to the process that you take electrons out from a species. Okay, so usually the first ionization energy is larger than 0, which means the process does not occur naturally. You need to provide some energy to it. And for the first ionization energy, the bigger the atomic size, the smaller the ionization energy is. So it's also easy to understand, if the size of the atom is bigger, the electron is far away from the nucleus, and then very likely the effective nuclear charge is smaller, so it's easier for these electrons to be pulled away. So if we look at the periodic table, we would expect from left to right, the atomic size decreases, so the first ionization energy increases. And from top to down, the atomic size increases, so the first ionization energy decreases. So this, like, theoretically should work like this. But if you measure the real first ionization energy of all elements, main group elements in the periodic table, there are a few exceptions. So the exceptions are in the period 2 and 3. There are dips in the first ionization energy at group 3A and 6A. So in other words, from left and right, the ionization energy should increase in each row. But for 3A group element, boron and aluminum, the ionization energy is smaller than expected. And also for oxygen and sulfur, the ionization energy is smaller than expected. All the rest follows this trend of first ionization energy. You may ask, well, first ionization energy, is there any second and third ionization energy? Yes, they are. So they called successive ionization energy. For barium, it has 3 electrons. Oh, sorry, it has 4 electrons. So we have first ionization energy, second ionization energy, and third ionization energy. So it just refers to the energy taken away from the first electron, the second electron, or third electrons. But if you look at this electron configuration of barium, so it's helium and then 2s2. There are 2 electrons in the 2s, and then will be electrons in the 1s, right? And you can see there's a huge jump from the second ionization energy and third ionization energy. That huge jump corresponding to a different principal quantum number. Now before you were removing electrons from 2s orbital. Now the third electron is actually from 1s orbital. So when you're removing an electron from different orbitals, a different principal quantum number, there's a huge increase in this ionization energy. So you can also see that trend in table 8.5, successive ionization energy of the elements lithium through sodium. So lithium has 1, 2s of electrons, and then two 1s electrons. So if you take away, moving from the 2s to 1s orbital, there's a huge jump. We talk about barium, and for barium, the same, moving from 2s or 2p, so two orbitals, basically, two level orbitals to one level orbitals, there's a huge jump. The same with carbon, nitrogen, oxygen. So this level, this trend is true. And also for sodium, although it's one row higher, we are jumping from 3 orbitals to two level orbitals. There's also a huge jump. And actually from the two orbitals to one orbitals, there's another huge jump. And also there is a huge increase of ionization energy when moving to electrons that have another principal quantum number. Okay, so from this table, or give you a sequence of ionization energies, you are expected to know what are the valence electrons. So electrons with the highest quantum number, principal quantum number, and then can identify which element it is. Okay, so identify the name of a period 3 atom based on its ionization energies. So it gives you a table of ionization energy. IE1 equals to 1012, IE2 is 1903, IE3 is 2910, IE4 is 4956, IE5 is 6278, IE6 is 22230. Which one of the element it is? Okay, so if you see the sequence of ionization energy, the IE1, the first ionization energy to the fifth ionization energy, they all in the same order of magnitude, a few thousand, 1,000, 6,000, a few thousand. However, the huge jump comes from 5 and 6. When we move into 6, is not a few thousand, it's 20,000, right? So here's where the huge jump is. And that means we have 5 electrons that are in the same principal number. And when we move to 6, it's another principal number. Okay, so in other words, we have 5 electrons in the valence as a valence electron. In the period 3, if we have 5 valence electrons, that means we have phosphorus as the element. We also need to talk about electron affinity. So it's another concept. Electron affinity, or EA, is an energy change accompanying the addition of 1 mole of electron to 1 mole of gaseous atoms or ions. So it's actually the opposite as ionization energy. Ionization energy is removing an electron, and this electron affinity is adding an electron. So after ionization, you create a cation. After electron affiliation, then you have anion. So it's just the process is different. Yeah. And in the periodic table, we talk about trends, right? So for electron affinity, we expect it to increase from left to right. However, it's not at all regular. And from the top to down column, we expect the electron affinity to decrease. However, only group 1A follows this rule. So it's, in other words, it's pretty random. We don't see a very good trend of electron affinity of this atom in the periodic table. However, there are general patterns for electron affinity. So reactive nonmetals in group 6A and 7A, they are reactive nonmetals. They have high negative electron affinities. Okay. And for reactive metals in group 1A and 2A, pay attention, it's reactive metals. Okay. 1A and 2A, they have low negative electron affinities. So these two are the general patterns of electron affinity. All right. And also, finally, Noble gas in group 8A have slightly positive electron affinities. So it's so stable, it does not want to be add another electron. So it's positive value. Yeah. With all of this, we talk about many trains in this video, but that's all we have. And I'll see you next time. Bye.